Fun with Markov Network Brains, an introduction to evolutionary machine learning using ES6 in browser for dummy programmers, by Jeffrey Cave on August 23, 2019. Link in the description. Over the course of about 1,000 generations, a Markov network brain evolves dumb bugs on the left into something capable of finding food immediately on the right. The bugs achieve this with no awareness of their environment beyond their physical bodies or antennae. Please click for the demo, and refs and links in the article reveal relevant code samples. A couple of months ago I was at a wedding, and naturally the conversation turned towards the capabilities and limitations of artificial intelligence. I'm not an AI expert, and my exposure to it has been sketchy at best. I have implemented algorithms, but I've never really done a deep dive into any of them to really understand the mechanics. So when the conversation brought up the concept of genetic or evolutionary algorithms, both myself and the other fellow had to confess that we really didn't know that much about them. What little we did discuss got me curious, and on the plane ride home I came across an article on Markov Network Brains. When I first read about Markov Network Brains, something very deep resonated with agricultural and medical experience from my past, and I wanted to go deeper into the mechanics behind them. A gut feeling of familiarity was only enough to whet the appetite. What I really needed was a simple implementation that I could step through to observe the changes as they happened. I'm a fan of browser-side JavaScript for solving problems. There's always a compiler and a debugger handy, so I was fortunate to stumble across an incomplete JavaScript implementation on GitHub. My initial intention was simply to step through the code to understand the process. However, after addressing a couple of minor visual bugs, I found I had over-tinkered, leaving me with some heavy lifting to get it to work. A deep teardown was necessary and resulted in a fun little simulation. What better way to really understand what was going on? A layman's description. Markov network brains are evolutionary algorithms that are based on the modern models of genetics and evolution. The same natural processes that allow bacteria to become drug-resistant can be used to breed animals to a specific purpose, or to breed a computer program well-suited to solving a specific problem. The point to any software algorithm is for the machine to learn to solve a problem. In traditional programming, we do this by having very clever humans write a computer program that inspects some set of the input values and creates a new set of outputs. Technically, this is the definition of a function. Markov network brains, really machine learning algorithms in general, are no different. We have a problem that needs solving, a process for solving it, and we base it on some inputs. What differentiates MNB, Markov network brains, is that we do not directly create the program. Instead, we allow it to be randomly generated, and then slowly bring it closer to solving the problem by automatically testing small random changes. Actually, when we phrase it that way, it doesn't sound that different at all. There are three interrelated but independent components that are important to understand with Markov network brains: the genome, the brain, and the breeder. The ability for the algorithm to learn, become better able to solve the problem, is tied to the way these three components work together. The genome. This is like the programmer's uncompiled code. The brain. One could think of this as an executable compiled software. It also has memory allocated for storing information. And the breeder. The breeder is the developer that judges whether the code is successful or not. Like any software, these three parts are distinct, but strongly interrelated. Also, like any software, the interesting part happens at the transitions between the parts. The genome is initially created as nothing more than a random array. This, like a DNA genome, is a list that will be used to create actors. In our case, it will be compiled into the brain. The genome to brain transition. A genome is compiled into a brain by reading the genome and using the data as the basis for allocating a quantity of memory, initializing the memory values, and allocating transforms for the memory. The transforms, or gates, are predefined functions like OR, AND, or XOR transforms. Other transforms are possible. Please use your imagination. Lastly, the genome is used to map memory elements as inputs and outputs for each transform. Remember that these values were randomly generated, so, at least on the first pass, these transforms, as well as the quantity of memory, are selected randomly. Basically, you have generated a completely random program acting on random memory elements. Now when we transition from brain to breeding. Once the brain has executed, it will have generated some outputs. It's up to the breeder to judge whether these outputs were of any value or not, or more importantly, which of these executions was the most valuable. In a more complex environment, it is also reasonable for the breeder to observe the brain in action. To achieve this, we need to run several different brains many times. Out of these many runs, most will be useless, but some will actually be useful. Like an animal breeder, we can select the most useful of these genomes, and use them as the basis for better genomes, discarding the rest. Once the breeder has selected the most successful of the programs, these programs can be used as the basis for trying new variations. This is done through a reproduction process where genomes are randomly intermixed with one another, basically sexual reproduction. This produces a new algorithm that has a new mix of decision-making processes. The key is that each of these newly created genomes is a little less random than its predecessors. Good decision-making structures are kept, and bad ones are culled. Genomes identified as good are recombined with one another to see if they result in something even better. Over time, this process will result in progressively improving programs that get closer to solving the problem. Looking at the results from that initial run, we can see that a second plateau gets reached around generation 120, before the last improvement at around generation 230. Due to the element of luck, a different run on the right took nearly 10 times longer to discover that second plateau. As with any system that has randomness involved, debugging can be painful. There's always a question of whether an observed behavior is a result of luck, good or bad, or faulty programming. The problem is most observable with bugs being randomly placed right on top of the food, and then doing nothing. These bugs receive high reward purely based on luck. Bugs that are actively moving in search of food end up being culled for not being as successful. This element of luck is undesirable. A lucky bug, the blue bug, has no neural activity of any kind, but was randomly populated right on top of the food source. As a result of pondering this problematic element of luck, two unique additions were added that were worth noting: culling of useless brains and reuse of successful genetics. Both of these are based on animal husbandry practices. If the randomly generated program does not result in any output, it is of no value to us. Basically, if the animal's brain dead. The brains created are constrained to an array of approximately 50 elements of memory. Given 3 outputs, that is only a 6% chance that randomly generated programs will result in any meaningful output. Larger memory will make these odds even worse. To overcome this, I ended up creating a check in the generation routine. Immediately after creating a random brain, its transforms are scanned to determine if they will ever result in any action. If none of the transforms in the brain ever write to the output segment, the bug is immediately discarded and a new bug is generated in its place. While investigating the element of luck, it occurred to me that animal breeders keep track of their most successful breeding stock. Animals with good parentage are likely to produce better offspring than animals with poor parentage. To simulate this, I introduced a concept of karma. Karma is a score that is attached to the genome rather than the bug itself. It is calculated at the end of the cycle by taking the bug's score and averaging it with the genome's score. Newly created genomes inherit their predecessor's karmic score by averaging the score of the parent genomes. If we look at the diagram, we can see that going from left to right, we can observe bug brain activity. On the far left, we have the genome's karma, the bug's current score, blue is better, the inputs of the bug's sensing bodies, sensory organs, a color code that changes depending on the current state of the memory, the bug's brain, and the outputs being change the speed, either speed up or slow down, speed lean to the left or lean to the right. When it comes to time to compare the genomes for effectiveness, karma is used. By evaluating the overall genome rather than the bug itself, this allows for genomes that are unlucky to get another chance to prove themselves. Continued lack of success will result in karma slowly declining, eventually resulting in a cull, while a single bad generation will not cause an otherwise successful genome to be lost. Unfortunately, I have no clear evidence that either the early culling or the karma actually were useful. These were introduced to compensate what turned out to be a defect in the brain processing itself. While logically sound, the only evidence is the long delay in the very first generation that gets created. This long delay is partially caused by thousands of bugs being rejected. I can only imagine what running each of these useless bugs through a couple thousand cycles of activity would cost. At some point in my reading, I came across a statement that evolutionary programming has low value because similar results can be achieved faster using other techniques. There's also a counter-argument that they can discover solutions that humans are unable to consider. This may be true, but I had a lot of fun building the simulation, and I'm still fascinated by Markov Network Brains. Writing software is itself enjoyable. There's a beauty and elegance in the process involved that sometimes gets lost in work deadlines and customer expectations. Sometimes the act of writing software is just an expression of beauty and creativity. Playing with the simulation was just that, a bit of art for art's sake. From a philosophical standpoint, the act of truly understanding the evolutionary process involved in this algorithm has given me a new perspective on the complex self-forming systems that are all around us. From interpersonal relationships in the office, to black market economics, to the way students learn, to political alliances. I now just see it slightly differently than I did before. It was interesting to watch my own biases in decision-making. My original hypothesis was that bugs would evolve a spiral search pattern, and what I perceived as a defect in their behavior led me to increase punishment for touching the boundary in an effort to force them to conform. In the end, I was surprised to wake up one morning and discover the bugs had evolved a pattern of ignoring the pain and using the wall as a way to orient themselves in their environment. Turned into my own little Stanford experiment. Lastly, this project has been a reminder of how useful it is to build throwaway programs. When learning something new, it's far better to build a small piece of code than to tackle a giant program. Lastly, this project has been a reminder of how useful it is to build throwaway programs. When learning something new, it is far better to build a small piece of code than tackle a giant problem. A small, simplified model can be held in our head while you learn. When your organization requires reliable solutions, reach for a battle-tested library. But when you want to understand, build from scratch. To quote Feynman, "What I cannot create, I do not understand." Ironically, maybe poetically, I found that quote via Chris Adami's blog while searching for references for this article. Adami is the guy who started this whole mess for me. Deep understanding is a funny thing. Sometimes you come to learn that the battle-tested library isn't as useful as you thought. If you're interested in Markov Network Brains, you should 1. Open the simulation, press F12, put a break somewhere in the code, and start stepping through it. Stepping through running code and observing the changes is the best way to learn about a program's behavior. You should also fork and fix the code. A coworker was recently asking me about this program and started suggesting all kinds of great ideas I could implement to make it more interesting. Suddenly I realized I had taken everything I wanted from this little toy. I'm going to move on to other projects, and instead I suggest he should make the changes. Fork the project. Fork it from the same point I did and build it up yourself. Fork my version. Make a cool modification. Either way, I'd love to see what you come up with. You could change the physics, make collisions, spherical world, make the bugs aware of one another, watch competitive behaviors evolve, maybe some cooperative behavior. Find a more challenging problem for them to solve, randomize the food, introduce fight and flight to make them prey. Put the brain in a separate actually, somebody please do this. Put the brains in a separate thread. Or on the GPU. Those would be excellent changes. You could introduce probabilistic logic versus the binary logic I used. Trust me, this list could go on forever. You can also read more about Markov Network Brains from people that actually know what they're talking about. I've taken some liberties with metaphors I've used. Learning the shared metaphors and terminology is probably useful. Go study at Adami Labs. The original article that I found. They also have a battle-tested C++ library available. JavaScript has brain.js, a library that implements MNBs as one of its models. Go read the Wikipedia article on Markov logic networks. Read about Modular Agent-Based Evolution Framework, MABE, in Python. It also offers a framework in Python for defining all the parts. And go read some comments on Reddit, which has a detailed criticism of evolutionary algorithms and computation by programmers. I hope you enjoyed. If you did, following me on Medium. Thank you.